So next presentation is by David Van Acker. David is a principal of CVM, King of Prussia in Pennsylvania, also past chairman of ACI 364 committee. So, David.
Thank you, Ashok. Well, hopefully you have the controls part of this worked out. So glad to see everybody here this afternoon. So I want to talk about Chapter 7 of the evaluation guide. It's really evaluation and assessment. And as we all know, concrete structures deteriorate. They exhibit a number of signs and symptoms that kind of express that deterioration or decay or distress. And it really presents challenges to the design professional on how to interpret those signs and symptoms, make sense of that, and apply remedies to their repair and rehabilitation efforts that are going to work. So what I want to do this afternoon is to show you some case studies. It's really divided into two parts. We're going to talk about non-destructive evaluation testing and how that assisted us in our evaluation, and then go on to look at how we make sense of that information in some a little bit challenging cases. Right. If I in the back, if the sound falls off, please raise your hand and let me know. So as we said before, structures deteriorate for a number of reasons. Sometimes it's just natural aging. Other times it's premature deterioration, degradation. It's exposure conditions that affect that. There's a number of things that can really impact that. Non-destructive evaluation techniques will be presented in the first half of the presentation. And the second part is really making sense of it. I mean, that's the way I look at it. It's really the proper diagnosis. Anybody that's been performing evaluations for a while, you commonly run across previous repair attempts that have shortcomings for whatever reasons. And sometimes it really is a misapplication. It's a failure to diagnose the problems properly. So we want to talk about that. Condition evaluations are done for a number of reasons, as we all know. You have deterioration or distress of a structure. There's accidents that occur, fires, natural disasters, simple things, as John Lund talked about earlier, with a change of use in a property that's going to inspire the performance of a condition evaluation, or sale of a property. Fundamentally, it's just essential that the design professional really understand the behavior of a structure. How is it expected to behave from a designer's perspective? How does the structure really behave under normal circumstances, under unusual circumstances? Enclosed structures could be in a pretty benign environment. Certainly you don't have the temperature fluctuations, usually the ranges that will affect it. But you do have operations inside. Storage type facilities that would have heavy loads imposed on them in a cyclic way. Exposed structures, as we all know, you've got the environmental factors that come into it, process-related factors that affect it, and you get into extreme loadings, accidents, natural disasters, things that may not have been anticipated when the structure was designed. Another important part about distress and deterioration, sometimes it's the interaction between systems that may not have been intended. Concrete structures deflect. Concrete structures perform in certain ways when you attach other systems to them, glazing systems. Perhaps the allowances aren't properly made to recognize the fact that that concrete structure is going to do certain things. So it may go back to some of the original design and construction issues. And here's just some examples of some of the loading environments and the things that influence the concrete structures. On the upper left-hand side, something everybody's familiar with, an abutment and a concrete overpass where you see the severe exposure from de-icer chemicals, the repeated cycles of wetting and drying and freezing and thawing in a rather moist condition. On the right-hand side, we all know we're supposed to design concrete structures for snow loads. Sometimes we don't always get the snow loads right, but sometimes getting the snow off of structures is done in unusual ways that, again, it's going to stress a structure in a way that an engineer may not be aware of when they look at strange cracking patterns in a structure. The bottom one is just an industrial structure. You've got, like in silos, you've got extreme temperature differentials when you store material inside of it. Clinker silos as an example, and when you put material product inside of it, it's very, very hot, and the outside is really cold temperatures. So things like that will impact the structure. All right, so now let's get into some examples of how non-destructive evaluation, these are projects that we've been involved with where the evaluation has really helped us make sense and just monitor, in this case, monitor the structure in a way that provided useful information to us. So a little bit of background. This structure is partially old. It's exposed reinforced concrete structure, a waffle slab system with the beams all exposed on the outside, cantilever beams. Then you've got brick masonry construction on top of that for the facade system. About when the structure was maybe 20 years old, they had some condition evaluations done on it because of certain symptoms that were showing up. Unfortunately, they didn't really diagnose what was going on with the concrete for a period of time. Ultimately, what was happening was that there was alkali aggregate reactivity occurring in the concrete, and particularly the portions of the concrete that were exposed to moisture were really degrading from the inside out. And the unfortunate thing was a considerable amount of time passed, and the degradation continued at a fairly decent rate, so that at a certain point in time, it was really beyond doing much about it. So we came in very late in the stage, and our assessment really just did confirm the alkali aggregate reactivity. But at that point in time, it was determined that the structure really couldn't be salvaged. The owner wanted to keep the structure in service for at least another decade. So what we were really confronted with was how do we continue to evaluate and monitor the structure over time to assure the owner that it was safe, and until it got to a point in time where it was no longer safe. So on the left-hand side, you see what the AR looks like up close. You can see the cracking and fragmentation that's happening in the concrete. We've gone around the outside and installed screen and netting. It's shown on the right-hand side. Really had two functions. It certainly kept the fragments of concrete from coming off the face of the building. It actually did a pretty good job of concealing it. So when you walked up to the building, you didn't necessarily notice it. Excuse me. So it was ultrasonic pulse velocity and impact echo testing that we used to really establish a baseline of readings throughout the structure, going from the more exposed portions of the structure back to the interior of the structure. And we could take that information and, as we continued our monitoring program over time, we could really understand how the structure was degrading and what the impact of that was. So this is a broader scale picture of the structure on the left. One of the things that really started happening was the cantilevers started deflecting, and in the patterns of cracking that was developing in the brick masonry. In this case, we've gone ahead and we've actually installed steel columns underneath the cantilevers. They were not snugged up tight, so there were gaps to allow the continued deflection to occur. On the right-hand side, you see what we did was we went in through and installed strain gauges and installed data loggers and a monitoring system so we could just record over time what was happening to the structure. Basically, and we're still looking at it today. I think there's about another 5 years left to go in the owner's, at least the schedule that we talked about when the building gets taken out of service and replaced, but we'll see. Certain types of structures just offer more challenges to the design professional when it comes to evaluating them. Unbonded post-tensioning systems certainly fall into that category. We refer to it as kind of the engineer's toolbox, the techniques that are used to go about the evaluation of structures, chain dragging and sounding, very common methods, visual inspections. But when it comes to post-tensioning structures, one of the things that's used all the time, at least in our case, is ground-penetrating radar. As you saw earlier, it's very good at locating reinforcing steel. In our case, what we're interested in is not only locating the mild reinforcing, but the post-tensioning tendons. And I'll show you some examples of how that's applied here. This is just an example. Most people in the room recognize what an unbonded system looks like before the concrete's put into place. Just want to point out that ICRI has an excellent guide for the evaluation and actually repair of post-tension structures. So on the lower left-hand side, this is the technician running some of the, in this case, ground-penetrating radar. You know, the technology has gotten very, very good, and also the software to really make sense of the signals and the data that's collected there. So you'll see a diagram on the right. This comes from one of our projects where you see the reinforcing patterns inside. So the plan view is the reinforcing. It's mild reinforcing and post-tensioning. But you'll see cross sections on the bottom left and then over on the right-hand side. So it does a very good job of locating the internal reinforcing. I think the thing I want to point out is whereas it's good at locating it, it will also tell information very accurately, like what the depth of cover is, which becomes a thing. It will not tell you to a too high degree of accuracy exact size of the reinforcing, and unfortunately what it won't tell you is what's the condition of the reinforcing inside. And as all too often when you look at post-tension structures, you tend to see things like tendons that have failed that are protruded from a portion of the concrete. You see on the left-hand side protruding from the underside of a beam or a slab, or you'll see anchor pockets that are exposed where the grout confinement and protection has come out. And you see the lower right-hand side. This is a very common detail along the face of buildings, particularly high-rise construction, where all those anchors are, they exist along the sides of the building and all those exposed slab edges, and there's a grout pocket that protects it. But when you start seeing those pop out, you know you have to look in a lot greater detail. So the point I want to make is, whereas the GPR vital tools that we use in evaluating post-tension structures, what we're doing inevitably is we're going to go in and we're going to cut probe pockets so that we can examine the reinforcing up close. So in this case, we found there had been broken tendons that were obvious in the structure. We started looking around and running the GPR scans. We also found that there was cracking patterns that made sense for us to go look there. These were regions where the cracks tended to align with very low cover over the reinforcing steel. So you see in this case we cut it open. You see the epoxy-coated bar on the left-hand side and the pair of tendons on the right-hand side. But it's only when you get up close to it that you can see not only are you losing the protective coating on the mild reinforcing, but you're getting pitting on the post-tensioning tendons. Of course, now what does that mean? Non-destructive evaluation, there's a lot of great techniques out there, but the engineer always has to be aware of the fact that there are limitations to them nonetheless. This is a system that we had used a number of years ago. It's basically GPR based. And what they do is they scan the deck, they find the tendons, they run the scans along the top of the tendons, and they're looking for like a change in electrical resistivity coming through. And what they're really looking for is an interruption. Typically when unbonded post-tension tendons fail, there's a shortening that occurs, and so there's a big gap that develops in a given tendon. And what they're trying to do is to find that gap. You see on the left-hand side there, this is a typical output where they would identify, see where the signal drops off there, you have that gap in the curve. They would identify that as a break in a tendon. The limitations that we found in this testing was we ran these same scans over tendons that we know were broken, and they came up with data that did not show any of these gaps at all. So we really were perplexed by it. I think at the end of the day, they couldn't explain it. We ultimately reached a conclusion that the depth of field, the depth of penetration that they were getting with their equipment, it was not reaching the tendon zones in the bottom of the slabs. So We were hopeful that this was going to be useful for us to assess, the structure overall. It wound up not being reliable. So just word of caution that great technology is out there, but you still have to really look at it carefully and think twice about it. Of course, the best way to figure out what's going on with unbonded post-tensions and tendons is to cut them open and do pull tests on them. So it's the way that we find it's most accurate to assess the tendons. It's in cases where we know there's degradation, we know there's pitting going on. So we basically do tension tests on the tendons. I think the only downside to it is that you are cutting the tendons open. In the case of a parking structure like this, we're cutting them open in the most vulnerable zone. So it's not like we're enthusiastic about doing this. You can run these same tests on the underside, inside the building. We couldn't in our case, but it's probably the most reliable way to get some really good data on what's going on with the tendons. All right, so building structures are very, one way to assess those. Stadium structures present some additional challenges. Ann was talking earlier about historic structures. This structure just celebrated its 125th anniversary, so we've got some considerably old concrete here. We won't talk about those facets of it, but what we're going to talk about really is just the challenges of doing the condition assessment. The riser sections are pretty thin concrete. In this case, by design, they were 4 inches on the upper grandstand levels. In reality, they were only 3.5 inches, singly reinforced. Getting to the top surface wasn't a huge problem. The seating was in place. I think the real challenge for us was how do you get to the underside of it reliably to do any sort of evaluation, which really becomes essential. The key thing on not only evaluating a structure like this, but as you go forward and you want to do the repairs, you really want to get a sense of how much concrete are you really going to take out and repair. So you really have to, you can't just look at it from afar and come up with those quantities with any degree of confidence. So we did a couple of things here. GPR, again, we were able to run scans on the top of the deck. And really what we were looking for here was just depth of cover. We were not trying to size the reinforcing or anything else. So we basically went around and mapped all of the surfaces. So we knew how close the steel was to the concrete surface. This wasn't chloride-driven corrosion. It's all carbonation. We had done tests to determine what the depth of carbonation was. And once we had that alignment, we knew the areas where the probability of corrosion existed. So that was helping us really establish some sense of quantities. The other thing we did was corrosion potential measures, with copper sulfate tests. And again, we went around, we could scan the decks very accurately with this stuff and produce maps. So we were able to come up with zones and translate into what we thought pretty reliably were good concrete repair quantities. And of course, at the end of the day, that's what it looks like, right? There was a lot of concrete that came out, but the technology really helped us out on the quantities. I think it was tremendous for us. All right, now we're going to switch to the second part of the of my presentation, which is the making sense of things. So I said before, it's essential that the design professional really understand the behavior of concrete structures. Structures designed certainly from a strength standpoint, but other factors that come into design, things that really need to be considered. So creep, long-term deformation, particularly when you get taller structures that are going to shorten. You get volume change effects on the structures. So these are more serviceability things that have to be considered in the design, but they factor into the evaluation. Just so happens I have another historic structure here. This is actually a National Historical Landmark structure. Louis Kahn had done this. This is a research lab at the University of Pennsylvania. Unfortunately, the significant things about this was brick masonry, not concrete. But unfortunately, the concrete drove a lot of the distress in the building structure. So I said before about concrete creep and shortening. The towers on this are only 100 feet tall. So normally you wouldn't think there'd be a lot of issues with shortening of the concrete, that 100-foot concrete stack. Unfortunately, you also had 100-foot tall brick masonry that went straight up the building. It had relief angles in it. Unfortunately, when they built it, they really didn't provide any gaps between the relief angles in the brick. So you've got two things going against each other. You have the brick expanding from a moisture standpoint, and as any clay masonry product is going to do, and you have the concrete shortening. And when you put them together, particularly when you get to interruptions in that, you see on the right-hand side when they created some openings for windows and things like that, you could see from the ground where the walls started getting pushed out. There was a lot of distress that occurred at those geometry change portions. So diagrammatically on the left-hand side, basically what you had was you had that concrete core masonry stacking up. So as you went up to the parapet conditions around the top of the elevator towers and you looked at the copings, it was very clear that, so we calculated just approximately that between the concrete shortening and the brick expansion, you had 2 to 2.5 inches of differential movement in only 100 feet. And you get up to the top of the building and you look at the copings and you looked at whether some were still tilted, some had been picked up, and they had put grout under them in at least 2 instances. So we take our theoretical, calculations of this, or sort of just using empirical rules, and it's consistent with what we're seeing on the building, with the amount of movement that's happening at the top. Of course, that's what was going on at the parapets. When we started looking at some of the bulges in the walls, the photo on the left is a little bit hard to see what's going on, but essentially the diagram on the right is showing what happened. There was so much movement going on, and the upward thrust of the brick had actually deformed the relief angle. This was at one of the floors near the upper portion of the building. The anchors had failed, and the brick had shifted itself outward. And these walls were completely unstable. So we wound up taking off the upper floors of this, needless to say. The opposite was happening down at the bottom, where things were constrained. What you saw was a lot of brick fracturing that was occurring right in the relief angle lines. Now, the reason I mention this here is this is one of those symptoms that's easy to get misdiagnosed. A lot of people would look at this and they would see the corrosion of the relief angle, and they'll attribute this distress in the brick to rust jacking of the relief angle. It's not. Rust is really happening after the fact, after the moisture is getting in there and corroding the brick. The distress that's going on down here is driven by differential shortening. It's expansion of the brick and shortening of the concrete. Right? And again, some of the other things you see on the upper floors, this was over another one of those windows portions. When you look at cracking like this, people that do evaluations, they'll do crack mapping of buildings. This type of step cracking is commonly found when something is deflecting. It's easy to look at this and say, well, that concrete beam that's holding that up is deflecting. And that's consistent with that crack pattern. What's really happening here is you've got, it's hard to see in the photo, but the masonry, the brick masonry on the right-hand side of that photo, that's a stack of brick that's 100 feet tall. It's expanded and moved upward, whereas the brick on the left is only maybe 2 stories. So it's the expansion of the brick on the right-hand side that's dragging the rest of the brick up with it. Right? Not an easy one to, again, it's easy to misdiagnose that. You look at that at first pass and say, oh, that concrete beam's deflecting. Right? So you take that same concept of shortening of concrete, and that was only a 6-story building, 100 feet. Now we put it on an 18-story building. The order of magnitude is even more severe. I think the thing that they got going for in this building, they really did have the gap between the brick masonry and the underside of the relief angle lines. But at the corners, as you see there highlighted in yellow, that's where we found the most differential movement. Again, an 18-story building, those columns shorten to a certain degree. And when you don't allow the brick to expand at every floor, it just stacks itself up. Now, we did this assessment a long time ago before we had a lot of digital photography, so unfortunately I don't have any of those photographs. But when we cut open the parapets on the upper portion, there was a 4-inch separation between the top of the concrete roof slab and the underside of the inner width of masonry. The only thing that was holding the parapet walls on the building was the roofing. You can't strip in the roofing. So, pretty appreciable. All right, shift a little bit onto volume change effects in concrete structures. I'll show you a couple parking structures. There's a great guide. It was published by the PCA a number of years ago, but we find it very useful, and I think a lot of engineers find it useful in designing buildings and deciding where you should have and at what point you should have expansion joints in the structures. But these are sort of empirical guidelines. And I found over the years that you stretch the limits or people interpret these things differently. So there's a chart in there that'll, for different types of building structures, this is where you should have expansion joints, and maybe this is what the size of the expansion joints ought to be. So I found the guide good from a design standpoint, but when we look at structures, it's not uncommon that we find they either should have expansion joints in it and they were never put in it, which is the case on the left-hand side. This structure was not overly large. I think it's probably only maybe 200 feet in one direction, 180 in another direction. If you look at that table, arguably it wouldn't necessarily need an expansion joint, so it never had one when it was built. The reason for the yellow lines, so the yellow lines we'll talk about first. So the garage was maybe 20 years old, a lot of deterioration, distress. An engineer went in and recognized that it needed expansion joints, and so he put expansion joints in right where those yellow lines are. Now, putting expansion joints in a structure is not a straightforward thing. You got to think about how you're going to change the behavior of it. Nevertheless, they endeavored to put the expansion joints in. I think what happened was they didn't necessarily get them in there effectively, because when we came back and looked at the garage another 10, 20 years after that, where the orange lines are, that's where the garage created its own expansion joints. It basically unzipped itself. So, this is one of those ones of the adage where the structure really was smarter than the engineer that designed it. Picture of it. Again, we see this stuff in parking garages all the time. So there's two garages here. The one on the left is the older of the two. It pushes the boundaries of the size of a structure that that it's safe, I think, to do without an expansion joint. So the yellow lines indicate where they separated the main parking structure itself, precast, pre-stressed, double T's. They separated it from the stair towers in the upper left and right-hand corner. They separated it from the elevator banks at the bottom. Makes a lot of sense. The structure on the right-hand side was a parking structure that was added to it a number of years later. The area I want to talk about, though, is where the red circles apply. It's not unusual. You go through precast, pre-stressed structures, and you see failed sealant joints all over the place. And it's very common that you go through as a periodic maintenance program every 10 years, you replace all the joint sealants in the structure. However, when you start looking closely at the joints, you really need to pay attention to how are those seals failing and are other things going on at that. On the left-hand side, you'll see it's just a standard old caulk joint, face of the concrete topping up against the concrete column. But we suspected something more was going on here, and so we looked at it a little bit more closely. You see, then we cut a couple of probe openings around the column to look at the connections inside, and lo and behold, what do you find? So the column to girder connection on the left-hand side, even though the welds that you see there are not fractured, there were shear studs welded to the vertical leg of that angle that are embedded into the girder. They were gone. So that connection had completely snapped. There was a separation there. And that's consistent with the bars that you look at you see how the bars are bent? I think that was the continuity reinforcing that they were running through the columns, maybe to meet some code provisions. So once you cut things open, now you've got a whole different thing going on. You've got broken connections in the garage. So it's not a matter of going around and just replacing all the sealants in the garage. It's going around and making sure you understand that if these connections are broken, you can't just go and put sealant back. You've got to do something to the connections. Again, it's taking these signs and symptoms and making proper sense of that stuff. All right? Last one on the expansion joint side. This is one where they really got it right. This garage is over 400 feet long. They had 4 expansion joints in it. So you had cast-in-place concrete segments at the far ends, and you had a cast-in-place ramp segment in the middle. It's not a great parking design nonetheless. So they got the expansion joints right. What they did that was very unusual is that the precast segments in the middle, it's a single T system and the columns don't line up from inside to outside. So the precast system had no inherent lateral stability. What the engineer did was he put dowels to connect the precast segments to the cast in place. So they transferred all the lateral shear to stabilize and hold the precast system up. They relied on the cast in place segments to do that. Novel idea. Unfortunately, you put all that critical reinforcing through a moving joint. So needless to say, the water got in the yellow joints there, corroded the steel. One engineer came along and started cutting all the reinforcing, not really paying attention to the fact that, they were just trying to free the garage up to move even more so. So, needless to say. Fast. Mid-rise concrete structure, I guess this was the 20s and 30s. You've seen these before where you find all the degradation of the concrete, the rebar over the window heads. This was just some novel things so this building was converted from a light industrial use into residential in the 80s. There were a lot of historic tax credits around those days. So when we talk about expected service life of repairs, when we got into this, so they had redone this building in the 80s. You had another 20, 25 years on it. And we're looking at it, and the owner's just like, well, I have all this concrete degradation again. So we got up and looked at it close. What's not apparent here is they never did any of the concrete repairs back then. What they did was they took the concrete off of the rebar. They oversized the metal caps on the top of the window system, and they basically wrapped and they put welded wire fabric, or not welded wire, expanded metal lath, and they basically plastered it. The fact is they got 20 years out of the life of that repair. So I thought it was pretty astounding that it lasted that long. Our owner wanted 25 years, so we had to get creative in what we did. We gave him solutions. One was to go in and take the windows out and do the concrete repairs they really needed to do. He didn't like that at all. So we had to get a little bit more creative. So we wound up putting in a waterproofing system, sort of membranes there that we had attached it to the window system, regulated into the concrete. We used fiberglass panels on it, and it actually looks pretty good at the end of the day. The service life prediction on it, we think you get 25 years out of it. I would point that out just for the fact that the 562 code now does really require the engineer of record to inform the owner, very much so, what is the expected service life for the repairs that they come up with. And that's usually part of what's provided to them. You come up with a range of repair options, and it's very common that people put costs associated with those options, but it's of utmost importance that you really put in the service life as well. And obviously the costs are associated with that from a life cycle standpoint, but that's part of the decision-making process. All right. That's it. Thank you.